So today, chapter 23 and 24. So chapter 23 deals with reverberation and reverberation time. So in terms of that, I start out with this classic example of reverberation. And so in terms of Lou Gehrig and Yankee Stadium.
The news of Gehrig's illness stunned the country. And on July 4th, a huge, sad crowd packed Yankee Stadium to pay tribute to their beloved hero. Babe Ruth came back, and the two old teammates ended their long feud. Manager Joe McCarthy presented him with a trophy. At first, Gehrig was too moved to speak.
For the past 2 weeks, you've been reading about a bad brag. Today, I consider myself the luckiest man on the face of the earth. That I might have been given a bad break, but I've got an awful lot to live for. Thank you.
So you have to turn to that in the speech, as you can say. You can hear, in terms of the speaking, you can hear it in the background. Really, in terms of coming back and the speech as you went through. So in terms of reverberation. Reverberation time, right? So you turn to this one in terms of varying amounts of reverberation time.
Many factors influence speech intelligibility.
So no reverberation time. 0.6 seconds.
Many factors influence speech intelligibility.
Up to 0.8 seconds.
Many factors influence speech intelligibility. Many factors influence speech intelligibility. Many factors influence speech intelligibility.
And then lastly, you get 5 seconds.
Many factors influence speech intelligibility.
Basically, by the time you get to the last few, it gets really muddled and hard to hear what they're actually speaking and saying, right? So reverberation time. So you think in terms of something that needs to be taken into account when you are designing a space. Right? So in terms of reverberation time, in here. This is way off. So in terms of reverberation time, so the reverberation time, RT, will be given by 0.161, V, which is the volume of the space, and then A, which is basically the total absorption of the space. So in this equation, V, the volume of the space, is in terms of meters cubed. A is in terms of meters squared. They also, in your book, give you the formula if you are using our units. So they also tell you that RT is equal to 0.049 V over A. But now in this one, V is in cubic feet, A is in square feet. And really the difference comes down to in terms of the value for the speed of sound, whether you're using the metric speed or the R speed. Yes?
What's the V in A?
Volume of the space. A is basically the total absorption of all the materials in the space. So different materials will absorb sound different ways. Right? So you think in terms of something like concrete. If I have a concrete floor, how much sound is that going to absorb? Not very much, right? Hard surface, right? But if I have drapes on a wall, that will absorb sound, right? So different materials have different ability to absorb sound. And so have different absorption coefficients. So you think in terms of designing something like Benaroya Hall. You know, that's one of the things you have to be worried about was in terms of reverberation time. After all, you want to make it so when people are there listening to Beethoven's Fifth, they can hear Beethoven's Fifth, right? But also, because that basically is a multi-use space, you also have to think in terms of when there basically is somebody there who's giving a presentation. You also want them to be able to hear in terms of whoever the speaker is. For that, right? So basically there was a lot of money and time spent on designing that space before they actually built it. So figuring out what materials go on the wall, on the floor, the seats.
I saw a movie. It's an older movie called Hustle and Flow from like 2005 or 6. And these guys,
Great movie.
It's a great movie. They're poor and they're creating a studio in their basement. And this is before I started studying music. I noticed for the sound in the walls, they put old 8 cartons on the walls. I never thought of doing that. There's things throughout the movie I noticed that I would never notice before I started studying music. Like, for like a voice, a pop filter, they use an old nylon sock, stuff like that. But they put like on the walls.
That's basically what it is.
Yeah, that's basically what it is. But I would never thought of doing that. They put like A cards on the walls. It's just, it was just interesting. I just thought, like, because when you're talking about putting stuff for.
Right.
What's interesting too now is with foam, because they
Yeah.
buy professional foam, which is ridiculously expensive.
Right.
Yeah.
I mean, these things they sell kits.
Well, they don't have the money for that, just because.
Right. No, that's what I'm saying. But the
Yeah.
cool thing is that's actually they started doing that after because they've been using A cards for a while. It's kind of going through.
Right.
Oh,
Well, it's
yeah.
cheap.
Yeah.
And then they started emulating with this foam now. Now they're emulating in A card shapes.
Yeah.
For going on the wall.
Sorry to interrupt. It's just something I just.
That's a good point.
The absorption.
Alright. So in terms of this handout, basically this is a chart.
Already got it
Alright.
from Westwood.
In terms of absorption coefficients, right? So it has, in terms of this chart, a variety of materials. Right? You also have, in terms of the absorption, at various frequencies, because it does change with the frequency that's used. Right? So it is frequency dependent.
So a lot of these low frequencies, a lot of the low frequencies, they're not affected by different materials because they're so low. Like,
So what are you looking at?
because for
Flooring?
yeah, for the flooring, like carpet is 0.01,
Right.
and so is marble.
Right. But if you look at terms of seating, there's a big difference in the seating that you're using. So you think in terms of fabric upholstered seats are 0.49. So it does. Part of it has to do with upholstery. You got the foam in there and that sort of stuff in terms of your seat, right? Which helps to absorb sound. Okay. So basically, in terms of this chart, the lower the number, the more the sound is reflected. The higher the number, the more it is absorbed. Right? In terms of the way this works. Right? Right. So the way this would work then, in terms of designing a space like Better Oil Hall, basically they were concerned about what is the absorption across the entire range of frequencies. Right? So basically they would run this against the entire gamut to see what the absorption would be in terms of all the various frequencies for a given space. Right? But in terms of the way how this all works, in terms of designing a space, so let's say we have a space, let's do 40 meters by 25 meters by 15 meters, right? So that's my space for this particular hall, right? So first thing we want to know is what is the volume of the space, right? So if you think about a box, the volume of a box is given by length, width, height. All right, we got another one. Okay. Right. So the volume of the space is given by length, width, height. So we get 40 times 25 times 15. That gives us the volume of this hall. So that comes out to be 15,000 cubic meters. Right?
What does that say?
15,000 cubic meters. Again, volume is always in terms of cubic units, whatever those may be. Right? All right, so that's the space. So now the next thing is, okay, so you know how big the space is. Now you got to figure out, okay, what are you going to put in the space? So the materials you put in the space are going to have an impact on what the reverberation time is. Okay. So, for example, let's go through a bit of this. So, what do we want to put on the floor of this space? Huh?
Bamboo.
Is it on the chart? We want something on the chart. Bamboo's not on my chart. Again, this is now, you can probably find a chart that has it on there.
Tile.
But now, given that with the chart
I've
we
been to a
got.
studio with bamboo before.
All right. Vinyl tile?
Yeah.
All right. So we're going to go with vinyl tile, okay? And we're not going to do this for every frequency. We'll just we're going to do the calculation for the frequency of 1 kilohertz, okay? So we'll do it for 1,000, right? In terms of this, right? So we go with on the floor. We decided we're going to put vinyl tile. Okay? Now, to calculate the absorption of the vinyl tile, okay? The absorption due to the tile is going to be given by the coefficient, which is 0.03, okay, times the total area. Well, in terms of my dimensions, which dimensions do I need to use to get the total area of my floor space?
Length and width.
Length and width, right? So it's going to be the 0.03 times 40 times 25.
1,000 square feet.
Okay?
Wait,
And-
0.03 of that, so
Right.
30.
And that'll give us 30, right? So that's in terms of our floor. So let's go to the opposite side, which will then be the ceiling. Right? Because the ceiling is going to be the same dimensions here, right? 40 and 25. So we know that. So, all right. So what do we want to put on the ceiling?
Gold.
Meditech.
Gold. Oh,
Gold is listed.
You guys like the black keys?
Or
Hell yeah. Anyways, no, that would be pretty cool to have a studio that made of gold on the ceiling.
What would it sound?
I'm not sure. It might sound kind of cool, man.
Okay, and yeah, now if we can come up with the money to afford that, given that gold is on the order of whatever, $1,300, $1,400 per
It would
ounce.
just be gold plate, you know, like a quarter-inch thing.
Sure, Dr. Dre.
Okay.
Awesome.
All right.
No, I mean drywall.
So, in terms of our ceiling material, what do we want to, besides gold, what else do we want to put up on the ceiling? Because we want something we can actually afford.
Metal deck, 3 inches.
Metal deck, 3 inches?
Yeah.
All right. So we got that. So we got metal deck, 3 inches. We said 3 inches, and so metal deck 3 inches is going to be at 1K 0.89. So that gives us an absorption of 890. for that part. All right. Okay.
So you never times the height with it?
Not yet, because again, if I'm doing the
Flat
ceiling,
surface, two-dimension.
right? We just did the ceiling, we did the floor, right? Now the walls. Right? So, what do we want to put on the walls of this space?
Fiberglass.
Well, let's see, we got wall material. We got so you got brick, you got concrete, you got glass, you got plasterboard, plywood. Okay. Or reflective. What?
Plywood,
Plywood, how thick?
3/4 inch.
All right, plywood 3/4. All right. Now, what happens in terms of my wall space? So this is going to be 0.12, right? Now, what are my dimensions for that space? Right? So if you think about this space, right, go back up to the top here, all right? You think about, our room's a little weird shape, but we're going to have two short walls. We have two long walls for this, right? Right. So now the height measurement comes into play when I'm doing out my wall space, right? Right. So it's going to be, for this, it's going to be 0.12 times 2 times 40, and what is that? My height was what, 15? Plus 2 times right? So we got 2 long walls, we have 2 short walls, and then we want to multiply the absorption coefficient by the total wall area. And you end up at, we got a number?
How come you only did 2 and 2? Because like there's 4 walls.
There's two of these types.
Oh.
There's 2 of those types, right?
Yeah.
There's 2 long walls. There's 2 short walls. Right? What'd you get?
2,340.
How much?
2340.
Try again.
Yeah, that's not bad.
1950 divided by it's going to be more like 1,080.
Yeah. Wait. Yeah, 1950.
Well, that's the
Yeah.
that's the inside.
Yeah.
But then multiply that by 0.12, so 950.
Oh, it's 0.12, not 1.
1,120.
330.
Yeah.
234.
What?
Well, I'm glad we're all doing the same problem. I like that.
234.
Wait a second.
234.
234.
No, it's totally, yeah, 234.
234.
Totally.
Oh, right.
Yeah, because 10% would be 195.
It has to be 234, yeah.
Yeah, and then you take it to the 0.02%. We'll just,
Is that correct?
That is correct.
I think it's
234. Sorry, I was just trying to do it in my head.
You end up at 234.
That's an absorption coefficient.
Okay. So this gives us 234. Okay. That, right? Well, now we actually got to put people in this space, right?
What kind of people?
What kind of people?
There's 3 different types.
3 different kinds of people. Okay. So we need seats.
Yeah, what if you mention or something?
So we'll use theater seats.
fabric.
Right?
Oh wait, are there seats?
Oh, yeah, we need seats.
Yeah, fabric.
You just stand?
Yeah, just stand.
Stand? You want them to stand?
Yeah, just stand. Save money.
Okay. Save money, right? You don't have to.
Yeah.
Yeah, we don't want to give them seats, right?
Better seats. You just stand up all the time.
We're gonna sit down and watch
I can't place this.
Okay.
Can't place I'm not paying for this.
Really awesome.
Yeah.
Alright,
So let's see.
So it's time.
Alright. So let's do theater seats, fully occupied wood,
Wood?
0.76 for the absorption. Right. So seats, wood, fully occupied. Which has a coefficient of 0.76, right? Let's see, given our dimensions, 1 meter wide, 20 that way. So let's say we're going to have 500 in our space. And that gives us 380. Right? Based on, right? 380. All right, so now we got all the numbers for our space. The next thing you want to do is find the grand total.
Wait, what about people?
Well, that's fully occupied.
Okay.
We don't want people. All right. So the next thing we want to do is add up our numbers.
1534.
How much?
1534?
1534. All right. So 1534. Okay.
Square feet. And the square feet.
Yes. Right. So now we can calculate the reverberation time for our space. So the reverberation time for the space, RT, 0.161, the volume of our space, which we said was 15,000, right?
Yeah.
Over our number we got, which is how much?
1534.
1534. All right. So you plug that in, and you get what would be the reverberation time for the space.
1.57.
All right.
Is that meters? Yeah.
The units here will be seconds.
Yeah, okay.
All right. we got a reverberation time of about 1.6 seconds. For this space.
So if we had drapes instead of plywood,
Right. So then you start playing with it. You say, okay, well, is 1.6 seconds going to be too much for what you want to use the space for? Now, do I remember in terms of that little sound files we did? As the reverb time got longer and longer, things got more muddled. Okay. And so, probably 1.6 would be pushing it in terms of what you would want for the space. Okay. So then you look at, well, what others? So basically we want to have more absorption than what we got. Okay. So you could look in terms of what other things you could do in order to increase the absorption.
You make everybody wear a really big jacket.
Okay.
Your own blanket.
But no, as you said, that's why you put drapery up on the walls, right? Because that will increase the absorption by doing that. Okay. All right. Okay. All right. So you have in terms of figuring out reverberation time. And so basically they went through all this calculations for Benaroya Hall. And figuring out the various materials that they were going to use, knowing the volume of the space. So they did all this basically on the computer, calculated it all out, built the hall, then checked the reverberation time in the space, and it basically matched what they did on the computer. That's all. That's what you get when you spend hundreds of millions of dollars, on your space, right? So you think in terms of like if any of you have a home studio, what do you got up on the walls? Sort of stuff. Like you said in the whatever movie you watched, right? Or material you put up is going to have an impact on the sound you're going to get. So they do give you a chart like the one I gave you in your book, but it's a very small chart. Okay. The one I gave you has much more in terms of various materials and such in it. You can find other charts that have more. Okay. The other thing we didn't put in here in our calculation is you also, in terms of the air itself, absorbs energy. So if you look on page 533, you have a chart on that page where the bottom part says air absorption in that chart, table 23.2 in the book. And so you've got that it's based on the temperature, so 20 degrees Celsius, and relative humidity. Okay, so on page 533, table 23.2, you have a part that talks about the air itself also absorbs some of that energy. Right? So it is temperature dependent. It is also dependent on the humidity of the air as to what that is. Right? Which we didn't take into account in our space. Okay? But again, depending on what you're doing, you may want to take that into account. question on that part. So next week there will be a test.
Is that exam 3?
It will be exam 3. Right? What?
Last week, bro.
Alright. Alright.
So, and then obviously that'll be...
That'll cover,
open
yeah,
book,
21, 22, 23, 24.
Open book, open note.
Open book, open
part,
note,
Open part.
15?
Now, we just did the last 4. Yeah. So yeah, we'll be on those 4 chapters. So you can expect that there will be a question on there where I give you all the information in terms of the room size. I also tell you in terms of the materials that are used.
How did you come up with the seats number? Because how did you figure out 500?
How did I figure out 500?
Yeah, if you go back a little bit, you were talking about the seats, and then you like figured out the size. I don't know.
I mean, you just like throw a number out there.
He just said there's going to be 500 people.
Right.
Okay, so.
But really, if you look in terms of designing a space, you can figure, okay, so you figure roughly
Right.
about how wide is a seat,
Sure.
right?
I'm just saying on the
Yeah.
test, are you going to let us?
I'll give you the number, yeah. But even if you look at buildings, one of the things you'll see, depending on the wall, if they have it posted, and they post
Maximum
it,
capacity?
it should tell you how many people you can put in your space.
Yeah, maximum capacity, they'll tell you.
Right. Okay. And basically, it's all dependent upon the dimensions of the space. There's a formula that allows X amount of units per person, and basically you take your space, you divide it out, and you get that number. Is what you do. Okay. Basically, what I did is I figured out in terms of how I quickly came up with that. Is okay, you figure out a meter wide for a seat, and you got to have. There's going to be a front cushion for where the stage is. Side cushion for the aisle. That's where 500 came from. Okay, you put this many wide, go this far back. There you go. Okay. So in terms of your space, okay, so you're thinking, well, what do we want to have happen in our space? So what's the criteria? All right, so
You want the sound to travel equally so everybody can hear it.
right, so you want everybody has to be able to hear it, right? So whether you're up front or up in the farthest reaches of Benaroya Hall, that everybody can hear whatever is going on, right? Right. So we want to have in terms of adequate loudness, right? Again. After all, you got not everybody can afford the best seats in the house, right? You do have people who are going to be up in the upper tier, way back, right?
You gotta keep that in mind.
And you got to keep them in mind, because after all, they did pay money for their tickets too. And they're not going to be happy if they paid the money and they go there and they cannot hear what's going on. So you've got to have in terms of, can everybody hear in the entire space?
In Royal Hall, is it all just acoustic space, or like do they have speakers that produce the sound out of the audience?
So in terms
I'm pretty sure they might have, like, even Bitter Royal Hall, they have had conventions or, like, you know, businesses rented out where they have, like, a PA system, someone speaking, that kind of thing.
Right.
But generally, it's pretty like a
Right.
concert. You know, I mean, there's normally an orchestra or symphony there, which
Right.
are amplified anyways. But I'm sure there's times they use PAs
Right.
there, for sure.
Because I know, like, if you have like long enough hall, like you need like speakers
Right.
for
Yeah.
that too, like with the delay.
Right.
I don't think it's a normal setup they have though. You know what I
Right.
mean? I think it's something they have. Well, I mean, a good example. Well, the final projects, the graduation portfolio presentations, They have PAs there.
Right, yeah, because,
You know, but it's something that's not there all the time. They can install.
because generally it's the orchestra, is what the most primary use of that space
Good question.
is Seattle Symphony.
There must be some type of formula when they're doing PAs.
Is there a delay issue, like if you're sitting in the back, like completely acoustic concert, like if you're sitting all the way in the back, would there be like a huge delay issue? Like,
What's the dimensions of that space? Maybe a little delay, but I wouldn't notice it. It's not a huge space.
Probably not going to be as bad as like, say, a concert.
Well, when you have graduation, we'll be there. They use the space there.
Send them back, I'll let you know.
Easy still to come.
It looks too fancy for you to go there, okay? All right? So we want to make it so that, family, everybody can hear, right? Right? The other thing you want to have happen is that whether you're in the front or in the back, basically everybody hears the same thing, right? So we want the sound to be uniform. Okay?
Isn't that also up to the engineer too that's there?
Right. Right. So we want the sound to be uniform throughout the hall, right? So basically, whether you're in the front or in the back, you ought to be able to hear the same thing emanating from the Seattle Symphony, right?
Oh, that's true.
In terms of all the various instruments, all the various parts. You're not missing out, like on the violin section or something like that, during the playing of the concert. Okay? Okay. Okay. Also want in terms of clarity. So that's where you get in terms of the whole idea about reverberation time. Okay? Again, as the reverberation time gets long, you start getting where that sound coming back is interfering, and you get that whole muffled sound like we heard in the little audio clips. And then again, people aren't going to be happy. Okay? So in the chapter, they do talk about that one hall in New York City that they built. It was messed up, okay, in terms of all the acoustics of the hall. They really then had to spend money, go back in, basically rip it all, rip the insides out, try again. Okay? Right. So they do talk about, I think it's Avery Hall in New York. Right. So the other thing about it in terms of this list they give you in the book is in terms of aliveness. Okay? Of the sound. Okay. So again, what they say in terms of the book of definition of this, the listener should feel bathed in sound from all sides, but at the same time be able to localize the sound source. Okay? So you do want some reverberation,
Right. That's what
but
they mean
you
by
don't
liveness.
want overkill.
That's what they mean by liveness, though. We don't want it to sound dead.
Right. So you don't like that first sound file I played, that plant that had no reverberation time, right?
Yeah.
You don't want that, but you don't want 5 seconds either. Okay.
Could you like make like ventilation holes for like sound to escape, so you like get rid of some of that extra reverberation? Oh yeah.
Right. Right. Okay. And then we don't want echoes. Okay. In the space. Right. So you don't want to be in an echo chamber either. Right.
Isn't it up to the engineer to make what's this? It's up to the engineer to make sure all this stuff is properly managed and you know, make sure it's how do I say it?
Yeah.
To make sure that it's used properly, or that it functions properly, correctly. Isn't that correct? Like it's up to the engineer to make sure that all this stuff goes as planned or is functioning properly. To make sure that there's not a lot of echoes. To make sure that the sound is uniformly heard across the given area. Isn't that true?
Yeah. So you think again, you go back to again, Ben Royal. It's everything. Yeah, you got the project manager, engineers, the computer people. That basically their job was to make sure that in terms of the sound quality in that space, that it was going to meet the criteria necessary for a symphony orchestra to play in there and everybody to hear everything accurately. Okay? And again, it was all done on computers first.
But it's all done on computers first. Huh?
Right. Because barely you know, if you're, it's far too expensive to build it, then find out it's messed up, have to rip things out and start over again, okay? So again, everything gets done on computers first. You know what you want to use, okay? You design it, you build it, and then, like I said for Benaroya, they did all that, and then they tested it, and it basically matched what they did on the computer. Okay, so that's, again, you're spending that kind of money, you know, you better get what you paid for. Okay.
When did they design that? Or when did they build it?
Well, it's been there a while now. I'm not sure when it was up, but it's been there a while. So look it up. But yeah, right? So in terms of, so then they talk in the chapter, they talk about concert halls. And so you think in terms of going actually someplace for a concert. So they talk about various qualities you want in a concert hall. So intimacy, even though it's a large space, doesn't seem like it's a small space. You don't want it to seem like you're really far away, okay?
A good example is the Paramount Theater.
Okay.
You walk in and it's just, yeah, it feels a lot more intimate than it, you know, it's big. It holds a lot of people, but it's feel up close and personal.
Okay. Right. Again, reverberation, liveliness of the space, like we had before. Okay. Again, you want the right interplay of the two. Spaciousness. Does it seem like the music is coming from a larger space than what it really is? Again, all these are given in the book on 535. You go through the various properties. Clarity, again, in terms of sound. Warmth of the sound. Okay. So warmth deals with the bass part of it. Okay. So warmth deals with the fullness of the bass tones. Okay. Okay. Loudness, balance. So is there balance in the tones? Blend. So in terms of the mixing of the sounds, and then in terms of the people actually up on stage, in terms of ensemble, so badly in terms of the performers being able to play well together and play off of each other. You got to worry about in terms of the hall you're at is background noise. Right? What other things are going on? All right. So you think in terms of the heating and air conditioning system. Is that, when the heat comes on or the air conditioning comes on, is it going to disturb the people who are in the hall listening to the music? All right. Outside traffic noise. Does that bleed into the hall? Does the underground bus tunnel noise? That's all you think about where Benaway is. It's over the bus tunnel. So you want that none of that noise makes its way into that space. So yeah, the chapter finishes off with Avery Fisher Hall. Again, that was the one in New York City that they had all kinds of issues with. And then you think about other places where you think about sound. So you think in terms of churches and how they're designed. Classrooms. So you think about in terms of this space and the sound design of this space. That's all we get to listen to the traffic.
Was there sound design?
In classrooms, no, really they're not, right? Mainly they just put them up, put the tables, the desk in there, and there you go, right?
It's a good box.
It's a box, right? It's a box, you put the board up on one wall, you put the tables in, you call it good, right? So yeah. Man. So yeah, you think about here, we got the traffic there, and then if you're on, every once in a while you get the train goes by, and then they decide to blow their whistle, right? And then you can't hear anything until they go by, okay? So you got that all that sound basically makes it into the space. Okay? And you get the noise from the projector, the fan going, the noise from the heating air conditioning system going, depending on what's going on in the other classrooms. Up and down the hall, you have that noise comes in. You do get some noise from the shop area, where that was one of the things about putting that in over there. Is again we're supposed to, in terms of do some sound abatement for that space, so that if you're in the classroom next door or underneath that space, you don't hear all the noise from the saws going and all that stuff, right? So you try to minimize that. Right. Yeah, classrooms, there's not much goes into it, in terms of designing the space, all right? Yeah, okay. All right. So in terms of the chapter 23 questions, the exercises, number 1, they really just want you to calculate the absorption. They tell you the amount of wall and the amount of carpeting. They give you that number. They just want you to do the calculation for 125 and 2,000 hertz. And for that one, you want to use the table they gave you in the book. Okay? That way when you try to check your answers in the back, it'll match. So you use the table they give you in the book. So that table is on 531. So really, all you got to do is take the 100 and multiply it by the appropriate absorption number. for those. And that one they want you to do it for 2 different frequencies. Okay? And that's all they're looking for. The other question you got in terms of the exercise is talk about reverberation times for a concert hall to be used for orchestral music. And they tell you the size of the space. Okay? And so on page 534 at the bottom, so 534 at the bottom of that page, you have a chart, a table, that basically gives you in terms of different types of music and talking, right? So you'll notice if you read that chart, the bottom is in terms of cubic feet. The top of the chart runs in terms of cubic meters. And then to the left is the reverberation time. So you got to make sure you look at the right numbers. Okay? So the numbers they give you in the book are in terms of cubic meters. So you want to use that top scale and then go down where it gets to orchestra and then read across. In terms of that. Any question on that part? No? Okay. With that, let's take a little 10-minute break. We get up and stretch. Alright. The other chapter is chapter 24, and like I said, probably a lot of it, again, if you've taken live sound, those sorts of classes, you've probably seen some of this stuff already in terms of what's in this chapter. So this chapter does talk about speakers, speaker placement, power consideration, loudspeakers, directivity in terms of where's the sound going, so in terms of what type of speaker are you using, where's the sound going to go once you turn it on. And again, probably all stuff you heard about and seen in your actual audio classes. Feedback, equalization, time delay, so on, right? All those things you guys seen before? Talked about before in the audio, right? Audio classes, right? Yeah. So, in terms of the sound power level, so it does depend on the power and the directivity of the source. So, you do have one equation you will see in terms of metrics test. Here.